Swayam Prabha. Digital India. Educated India.
I welcome you to this lecture of flow through porous media, and we were discussing about heat transfer with fluid flow. So, what we have here is thermal equilibrium in flow through porous medium, which we have introduced already. So, what we discussed there is, if there is a flow through a porous medium and there is a differential element, so then we can write this as a governing equation, where this is the heat conduction through the solid. This term is responsible for heat conduction through the solid. This term is responsible for heat convection through the void phase. This term is responsible for the heat accumulation in the solid phase, and this term is responsible for heat accumulation in the fluid phase. Here the fluid is given a subscript G, which is basically gas is meant by G, and the solid is given a subscript R, basically rock is meant instead of the solid. So, now and we have discussed about what the implications of thermal equilibrium in arriving at this equation. We are talking about only single temperature field in this case, which is continuous. Now, if we look at the boundary conditions, what we see here is that at time t equal to 0, one can write that the temperature, which is basically this T hat is here the temperature is made dimensionless in the sense, instead of working with T in and T out. Okay. So, or let us say we have the initial temperature is T 0 everywhere, T is equal to T 0 at time t equal to 0. So, we write T hat is equal to T minus T 0 divided by T in minus T 0. So, in that case we can all this temperature inside this porous medium we can translate within a scale of 0 to 1, and that is preferred, because then when you go for a numerical solution particularly, then you do not your field becomes, the range becomes 0 to 1. It does not affect your accuracy in the computation. Similarly, here, so we can say that if this is the way we define, then at time t equal to 0 everywhere in the porous medium, for all x T hat is equal to 0, and for x greater than 0, time greater than 0 at x equal to 0, t is T in. So, if this t becomes T in, then this numerator and denominator they cancel out and T hat becomes 1. So, these are the two conditions one has, and then one condition we can bring in here. So, what condition we should put at the outlet? Okay. One condition you can put here is that there is no heat flow out from this, no heat flow out by conduction. Suppose I insulate this phase. Okay. So, by insulation I can apply. So, I can make sure that there is no conduction out from this phase. Basically, you can see this, since we are treating this as a one dimensional problem. So, that means these layers are considered, not only there is no flow out from this surface, also this surface, not only there is no flow out from the surface, there is no heat loss from the surface as well. So, if you want to establish this experimentally, then you have to take a porous block and put an insulation around. First of all, put some wrapping that will make sure that no flow comes out through the surface, no flow permeates out from the surface, and also there has to be an insulation, so that no heat can release from the surface. So, that is one assumption. So, similarly, we can put another assumption, that here we place at the outlet no heat flux through the solid phase. So, one can do that. So, then we will bring in k of the solid phase del T del x equal to 0, that means heat flux is equal to 0 at x hat equal to 1. X is again made dimensionless, x is written as x divided by L, let us say, where L is the length of the porous medium. So, x hat equal to 1 means the outlet. So, at the outlet you can impose that heat flux is 0. So, no heat is leaving the, no conduction is happening out from this, fluid can leave. Okay, this can be one boundary condition. Another form of boundary condition could be that at the outlet you hold a particular temperature T out. Okay. So, you can give then you give at x hat equal to 1.0, T hat equal to so and so, you can impose that as boundary condition. Another boundary condition would be that porous medium can be considered infinite. Okay, and definition of infinity is your choice. I mean, you what are the other dimensions depending on that. If the other dimensions are in micrometer, then centimeter would be or millimeter would be an infinity. So, then this at infinity you can assume that this front will never reach. So, at infinity one can say that at x tending to infinity the temperature is equal to T naught. Okay. So, temperature equal to T naught means T hat is equal to 0. So, this is also another type of boundary condition one can set. So, now if we look at how the solutions are, so these are the, this is how this was made dimensionless. I have it in this slide. You can see T hat is equal to T minus T 0 by T in minus T 0, x hat equal to x by L. T hat time also was made dimensionless, and this is the actual time divided by some way you can make dimensionless if you are looking for dimensionless time, and these are some of the parameters one can have dimensionless terms, and so this equation can be written in terms of dimensionless parameters. If we look at the temperature profile in this case, we first of all we have a single temperature field. Okay. So, single temperature field means temperature of fluid and temperature of solid at every grid, at every point, at every length, at every distance from the inlet, it would be a single value. So, now we see that as time progresses, first the temperature was 1, set as 1 at the inlet, and rest of the places are all 0. And then as time progresses, we see temperature is gradually rising. It does not mean, see, temperature has gone up to this place, it does not mean that the fluid that I am injecting in through this porous medium, that has gone up to this place. Maybe the fluid that I am injecting, that has travelled up to this point. It has travelled long far ahead, but the temperature front that is travelling, that will travel at a much slower rate. Okay. So, this is the temperature front position. Fluid front might have travelled already. So, then you find that the temperature is increasing gradually and at much higher time, and so here the time was made dimensionless in such a way that the T hat at 1.0 everywhere it would be same. So, temperature of the entire porous medium would be having the temperature at the inlet. So, this is how gradually the temperature will rise. This would be the same case for heat conduction in a solid plate, but here the mechanism is different. Here it depends on the velocity, here it depends on several other parameters. Okay, so, this is how I would expect the temperature to progress through a porous medium as the hot fluid is travelling through the porous medium. And this kind of this is a very common occurrence in many applications, that the inlet fluid, the injected fluid is at a different temperature. For example, if you go to this hydrocarbon applications, there this injection of heated fluid is extremely common in it, because the crude oil, it has a very high viscosity, and so it generally it tends to there is some difficulty in flowing that crude oil out from the porous medium. So, for this reason they inject hot water, they inject steam, they do in situ combustion, they do all kinds of things to increase the temperature, so that because the viscosity decreases with temperature. So, they have to increase the temperature surrounding the crude oil, even they use electrical heating also, electromagnetic heating. They use different forms of heating to make sure that the crude oil, viscosity of the crude oil gets reduced and the hydrocarbons start flowing. Of course, that flow there are a lot of other mechanisms there, because there would be, if crude oil is a mixture, and so some part of the crude oil which is the lighter fractions, that will travel. We briefly talked about it earlier when we discussed in this Kelvin equation, that the lighter part of the crude oil will travel ahead and the heavier part will remain there, and those kind of things. So, but this temperature profile is the flow of heat front along with the regular flow through porous media is very common in many different important applications. Now, when it comes to thermal conductivity of porous solid, I said that thermal conductivity cannot be same as the conductivity in intact solid, because of the obvious reason, because it is porous. So, had it not been porous, had it been intact solid, the grain to grain there is a much better contact. So, heat can flow much easily. So, or at a much higher rate. So, the thermal conductivity would be completely different. So, now if you introduce voids inside a solid matrix, so how thermal conductivity changes? So, in this regard, these are some of the models that are being considered in earlier considered by the earlier academicians. This is one is Ke, thermal conductivity of porous solid is written as the porosity multiplied by thermal conductivity of fluid plus 1 minus phi, which is the solid fraction multiplied by the solid thermal conductivity. So, that means here what is assumed is a parallel model for effective stagnant thermal conductivity. So, you are assuming there are parallel model for effective stagnant thermal conductivity. This is first of all, so few terms we are mentioning here. So, let us do this. Effective stagnant thermal conductivity. So, we are assuming there is no flow, stagnant thermal conductivity, there could be the heat can flow parallelly, one through the fluid which is occupying the void, and the other part is through the solid. So, these are two parallel channels through which it is flowing. So, effective permeability effective thermal conductivity is given by phi into Kf plus 1 minus phi into Ks. There could as well be a series model for effective stagnant thermal conductivity, and which would be defined by 1 by Ke is equal to phi by Kf plus 1 minus phi by Ks. So, now if somebody can measure this effective thermal conductivity, they will find that these are the two limits within which this thermal conductivity can be found. So, above two models provide upper and lower bound for Ke. There is another way another way this thermal conductivity is also presented, which is Ke is equal to Kf to the power phi and Ks to the power 1 minus phi. This can be done when Ks by Kf is not too different from 1.0. So, this is also another way of looking at it. Now, there are Ke as a function of phi can be determined experimentally. So, there is a way to determine thermal conductivity, and stagnant thermal conductivity you can very well measure using the same setup that is used to measure thermal conductivity, but instead of intact solid you can place a porous solid. So, it could be measured, and as porosity is varied. Okay, so, how thermal conductivity changes with porosity. So, one can find out thermal conductivity versus porosity plot and give put a correlation in that to find out for an unknown porosity what should be the thermal conductivity in that case. So, we must note that this thermal conductivity, there is no reason to believe that this thermal conductivity is simply the thermal conductivity of the solid material that is reported in literature. It is little different, it is a function of porosity. Next, what we have here is mean field model based on volume averaging approach. This is called non-equilibrium models. Non-equilibrium model. So, now we are talking about thermal non-equilibrium. Thermal equilibrium was that temperature of solid and fluid, they are same in this, and temperature, there is a single temperature continuum which is assumed in that case. Now, we are bringing in two different temperatures. One is temperature of the fluid, another is temperature of the solid. So, generally this is applicable more to structured porous media. Okay, and this is an example of structured porous media. Think of a honeycomb type structure, where these capillaries, they are running perpendicular to the screen. Okay, the capillaries, they are of size, let us say WF by HF, width versus height. Okay, WF is the width of the capillary through which the fluid is flowing, and HF is the height of the capillary, and these same size capillary, these are embedded inside a solid matrix, and the embedding is such that the distance between the two capillaries is on this, in the y axis it is HS, and in the x axis it is WS. So, WS, HS, these are distances between two capillaries. So, this is basically the solid part dimensions, and WF and HF, these are the fluid, the conduits through which the fluid is flowing, the dimensions of that is given by WF and HF. So, the x axis is given in this direction, y axis is in this direction, and z direction is perpendicular to the screen. So, in this situation, if you assume that there are, first of all, quickly we need to find out here the porosity of the flowing fraction, or that is what is the porosity. The porosity here is WF HF into, let us say, I have L is the perpendicular to the screen, we have, let us say, L is the length of this porous medium. So, then the total volume, if you look at that is, I mean, if I pick up one representative section out of it. So, that means, if I pick up one representative section out of this, so then this becomes WF plus half of sorry, this is WF, this is WS, distance between this and this is WS. So, this is half of WS to this side, this is half of WS to this side. So, this length would be WF plus half of WS plus half of WS. So, this length would be WF plus WS, and by the same token this side would be again HF is this dimension of this plus half of HS on that side, half of HS on this side. So, this side dimension would be HF plus HS. So, that side is WF plus WS, HF plus HS, and if L is the length perpendicular to the screen. So, then we have the total volume is WF plus WS multiplied by HF plus HS multiplied by L. So, that is the volume of the total volume of the representative element. So, I multiply this by L, and out of this representative element the void volume is, this is the void basically through which the flow is taking place. So, it is basically WF into WS multiplied by L. So, it is WF into HF, this side is HF, this side is HF. So, WF multiplied by HF, so that gives me and multiplied by L, L is perpendicular to the screen. So, that gives me the volume of the void in this total representative volume. So, this representative volume is repeated everywhere. Okay, so, that same porosity would be repeated. So, total that void volume in the representative element divided by total volume. So, this L will cancel out. So, WF HF by WF plus WS into HF plus HS, these gives me the porosity of the porosity, the void part, and then the solid part would be simply 1 minus phi f. So, this becomes the definition of phi f and phi s, the porosity of the void part and the solid fraction. Now, when it comes to the definition of rho f and rho s, density of fluid and density of solid, what is assumed here is, first of all, it is bulk density of fluid multiplied by the porosity, and it is bulk density of the solid multiplied by the solid fraction. This is required because you can see here they have not multiplied this part by the porosity term. I mean, this would have been much simpler if we had multiplied these by phi f and would have written it as rho f 0. So, rho f 0 C f 0, that would have been, so this is earlier, in earlier case, you remember in case of thermal equilibrium we had written del t multiplied by rho f, that there we had rho g C g and multiplied by the porosity term, because porosity term came because there is this accumulation happening, but accumulation is only happening over the void part, because it is within the fluid the accumulation is happening. Similarly, this accumulation is happening with the solid part in this case, del T as del T. So, naturally, they had taken into account 1 minus phi f term, but instead of that, instead of putting it 1 minus phi and considering this to be the bulk property, what they have done is they have incorporated it here itself and put rho f is equal to phi f rho f 0, and instead of rho f 0 phi f rho f 0, instead they are using rho f. Similarly, 1 minus phi f into rho s 0, instead of that they are writing directly the rho s. So, now if we look at what we have here, we have two equations, right, one for the fluid phase and another for the solid phase. So, one for the fluid, another for the solid, and there is some exchange happening. So, first of all, there are two different temperatures here, one is T f, another is T s, okay. And there is some exchange term here. This is the exchange of heat from solid to the fluid or vice versa, right. In this case it is T f minus T s, in this case it is T s minus T f. Okay. So, there is something called a heat transfer coefficient, which is important here. So, it is placed, and this is surface area per unit volume. This is how it is, the heat transfer is addressed from one phase to other. And there is one SC term dangling here, because this SC is in case there is any generation happening. Most likely we assume that there is no generation. So, this term is 0, and this is the way we have, they are writing this notations. It is rho del t of the, so this quantity is basically del t del capital T del small t. This we are already familiar with, and this rho f already has the phi term I have discussed. So, this is basically, this term is, when we bring in this t here inside, this term is basically talking about the accumulation in the fluid phase, and this term u I del x I of T f, okay, this term is basically the convection term. We had a convection term there. So, that same convection term we are putting it here. So, this term is basically, now outside it is rho f C f. So, we are talking about u rho f C f del t del x. So, this is the very similar term we had with convection at that time. And then we had, and mind it, last time the accumulation was on the right hand side. So, it has a plus sign, but now we have taken all of them on the one side. So, this is now, that time this was plus sign on the right hand side and this was minus. So, now we have brought everything together. So, now it became plus, and then this is the exchange term. This is the term that is arising because this is the heat that is given from the fluid phase to the solid phase, And similarly, when we look at the corresponding solid phase, we see that this is the accumulation term as before within the solid phase, and this is the heat conduction term. So, here also you may note that heat conduction in the fluid is not considered, okay, only the convection is considered here. So, this is the heat conduction in the solid term, and this is the heat that has been received due to exchange from fluid to solid. So, essentially now we are talking about a fluid phase temperature and a solid phase temperature, Tf and Ts. We have two continuum existing, one is the fluid phase, another is the solid phase, and as if there is exchange between fluid and solid, and this is that exchange term, and that exchange depends on what is the temperature difference between solid and fluid, or the corresponding temperature at that particular grid. Okay. So, that defines the exchange. So, this is, I mean, if you want to complicate this thermal equilibrium, if you do not want to consider thermal equilibrium, probably this is the first step. I will there are of course, there are issues, I mean, I have not discussed this term fully. I will do that definitely in the next lecture, because I will continue this to the next lecture. So, this is all I have as far as this particular lecture module is concerned. Thank you.